Remember, in the 11th grade, you learned that forces are classified into two groups. One group is you can apply a force on an object by contact, by touching. They are named as contact forces. For example, if you want to hold an object, you should keep this object in contact with your hand. Contact force is what you apply right now. If I want to pull this table, I have to first touch it. Contact. Then I should pull it. Contact forces. But in the nature, all interaction between two objects, not because of the contact. Examples. Sun attracts Earth. Is there a contact between them? No. Earth attracts Moon. Is there a contact between them? No. Electron, proton, positive and negative. They attract each other at distance. So there's no contact. They are not in contact forces. They are non-contact forces. These non-contact forces are named as field force at the same time. Field force. So field concept is provided to explain how two non-contact objects interact with one another. Field concept is provided to explain how two non-contact objects interact with one another, how they attract each other, or how they repel each other. We explain this by using field concept. There are three field forces. Until now, you learned two of them. One of them is gravitational field. Let's remember, gravitational field. It is the force between two objects which are at distance, like sun and earth, earth and moon. They attract each other. How? Without contact. How can we explain this? We explain it by field concept. How? We say that sun produces a gravitational field around. Remember the G equation? Which capital G. Mass of sun divided by R squared. So sun produces a gravitational field around. Yes, this gravitational field is decreasing as distance increases, but still exists everywhere. When another object enters inside this field, it will be attracted by the sun. So gravitational field is because of the mass of an object. Every mass produces a gravitational field around. Earth produces a gravitational field around, sun produces a gravitational field around, moon produces a gravitational field around, my body produces a gravitational field around, everything. So that's by using this gravitational field, by interaction of the gravitational fields, two objects attract each other. And gravitational force is only attractive, remember, in round 3 we talk about this. They only attract, they never repel each other. This is one field force. Another field force is electric field. A positive charge and a negative charge. How do they attract each other? How? How positive if they are of negative? How negative if they are of positive? By electric field. Every charge produces an electric field around. In the 11th grade you studied this. So for positive charge, electric field is radially outward. For negative one, it is radially inward. When you keep them close to each other, so these two fields, electric field, by these two charges interact, they attract each other depending on each other, repel each other depending on the direction of the electric field. If electric fields are in opposite direction, they repel each other. If electric fields are in the same direction, they attract each other. So then every charge, electric charge, positive or negative, produces an electric field around, and these electric fields interact, and electric force appears. Now third one is coming. Third one is magnetic force. So magnetic field is produced around a magnet. But what is the difference between this electric field and magnetic field? Electric field is produced by any charge, electron, proton, positive ion, negative ion, positive charge substance, negative charge. All of them produces electric field if they are charged. Yeah, charge means substance must have an excess positive or excess negative, not equal number of positive and negative. Equal number of positive and negative means neutral. But if positive charge is greater than negative, it is positive charge. If negative charge is greater than more than positive, it is negative charge. If substances are negative charge or positive charge, they will produce electric field around. There is no way. It will happen. But magnetic field is also produced by charges. However, these charges must be moving. Yani magnetic field is produced by electric charges which are in motion. So a magnetic field is produced by electric charges which are in motion. And so to understand why a magnet is a magnet, so we should understand where are the charges inside a substance? Where are they? Inside an atom. Where are they located? Inside an atom, where are positive charges located? In the center. Negative charges located around the center. So which one is in motion? The electrons are in. And protons are also vibrating, but their vibrational motion doesn't make so big a magnetic field. But electrons, they are revolving around the nucleus, at the same time rotating about their own axis. So these moving electrons inside an atom provides a magnetic field for each atom. Yeah, each atom behaves like a very small, tiny magnet with ample and S pole. Okay, now let's continue. So electrons are in motion in an atom, and electrons are in motion in an atom by two ways. One of them is electrons are revolving around the nucleus, just like planets are revolving around the sun. So revolving around the nucleus of the atom. Second motion electrons exhibit is rotational motion. They are rotating about their own axis. These two motions of electron provides a magnetic field for this atom, that atom. So these two types of motion of electrons provide a magnetic field for each atom. That's why we said each atom behaves like a tiny magnet with ample and S pole. Like that. I will represent them like this. It's an atom, generally spherical to show it. One side is ample, other side is S pole. This is an atom with magnetic field. But I wrote most of the atoms. Not inside, I don't write all. Why most? Because inside an atom, there is no single electron. There are sometimes more than one electron. 2 electrons, 5 electrons, 10 electrons, depends on the type of the atom. In chemistry, you learned that, huh? Electrons can be revolving sometimes like this, one of the electron like this, other one is like that. If they are revolving in opposite directions, they cancel one another's magnetic field. That's why some atoms can have 0 magnetic field. That's why I said that most atoms behaves like tiny magnets. Yeah, for most atoms, electrons' revolutionary motion provides a magnetic field in the same direction, and so they spark each other, and then atom has a net magnetic field. Okay? So most atoms behave like a very, 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 very tiny magnets with ample and S pole. Then domain. Atoms have magnetic fields, but there are billions and billions of billions of atoms inside a substance. When these atoms have a magnetic field in the same direction, they form domains. Domains are a group of atoms whose magnetic fields are parallel in the same direction. In the same direction. Look at that. This is simple. Just I draw. It's a drawing model. Of course, in the atom you cannot see their directions. But when the atoms have same magnetic fields, same directed magnetic fields, they form a domain. So, but it doesn't mean that all atoms are like this. There's just one domain. Billions of domains exist. Just like in this classroom, how many students? 27? 26? Some students are like domains. For example, they are domains. They move together. Huh? Their magnetic fields are parallel. Anyone who domains in here? Domains. Who are good friends and always going together? Huh? That's domains. Such are domains. So their interests are parallel. They make a group. So domains are like this. When the magnetic fields of the atoms are same, they make a group. And these groups are called domains. One domain, another domain, third domain, fourth domain, fifth domain, hundreds of them, thousands of them, billions of domains inside a substance. And depending on this domain orientation, a substance can be a natural magnet, or can be a magnetic material like iron, cobalt, nickel, steel, or can be non-magnetic material like a paper, plastic, wood, depending on what? Orientation of domains. If most of the domains are in the same direction, like this figure, see that? One domain, another domain, third domain, fourth domain, fifth domain, you see? So they are all in the same direction. So they support one another, then this substance will get a net magnetic field. Called as natural magnet. In natural magnets, most of the domains support each other. Maybe some of them will be weaker, but most of them support, and then results in a magnetic field. Then that substance becomes a natural magnet. But in some substances, domains are in random directions. Look at them. This one and that one, or they're same. This and that. Yeah, there are billions of them. So when they're in random directions, what will happen? They will cancel the effect of one another. So net magnetic field is going to be zero. In this case, it is not a magnet. What is it called? Magnetic material. It's called a magnetic material. Example, iron, nickel, cobalt, steel. And magnetic field materials can be attracted by a magnet. Magnetic materials can be attracted by a magnet. But there are a third group of the materials, which is non-magnetic materials. In non-magnetic materials, there are no domains. No domains are formed. Atoms have individual magnetic fields, but still they are in random directions. Still net magnetic field is zero. Non-magnetic field materials. Paper, wood, plastic, they are non-magnetic. And a magnet does not attract these materials. So then, these are the groups of the types of the materials, depending on their domain orientation, depending on if domain exists or not. Until now, this part is not explained in your book. This is not going to be direct question in ministry, but for understanding incoming part, these are needed to know. Now coming, from this point on, it's all are included. And that's why they are colored with the yellow avatar. Yellow part, you remember, it is there, which means it is not in the book, but important for understanding subject. Okay, from this point on, now we start studying your book. Magnetic hysteresis is the first title. Okay, what type of material is this? It's a magnetic material, like an iron, cobalt, nickel. How do you understand? There are domains. Yes. The domains are in random directions. So net magnetic field is zero. If we expose this magnetic material to a magnet, keep it close to a magnet. When we keep a magnetic material to a magnet, just like in my back, let's check if there's a magnet or not. And the magnetic material, a pin. I need a pin. Pin. Let's check, let's see it. It is a magnetic material. Oh, good. I need another pin. Thank you. Okay, we have two pins. A pin, magnetic material. Another pin, another magnetic material. Iron and iron, steel and steel, whatever. So they don't attract each other. You see that? Pin does not attract a pin. But I will make them attracting each other now. I will use a magnet. Pin attracts a pin. Do they? But more surprising, I will move this magnet away. Oh my God. So what's going on? Did we find the differential rules of the nature? No. This is a rule of nature. So what happened here? When I expose the magnet to a magnetic material, in a magnetic materials domains are in random directions, so the net magnetic field is 0. But when you expose it to a magnet, these domains directions becomes in the same direction. They become regularly arranged. So when they're in the same direction, the domains start supporting each other. Yani this iron becomes a kind of magnet. Not natural magnet, but a magnet, which is called in physics induced magnet, but your book doesn't talk about this. This iron becomes an induced magnet. So when we attach a magnetic material to this iron, then this pin it attracts another one. So randomly arranged domains becomes regularly arranged. So iron becomes magnetized. And then one pin attracts another pin. Another pin attracts another pin, another to another. It goes until the last one, which you cannot change the domains of the pin, so it's not going to be a magnet. Everything okay?
Yeah.
All right. So, but what happened is this: when you remove this magnet, pin does not lose its magnetic field very quickly. It takes time. So, when the external magnetic field is removed, the material, this magnetic material, retains its magnetization for some time. This phenomenon is called magnetic hysteresis. Now let's see what magnetic hysteresis is once again. Yes, a pin cannot attract a pin. Just show it to you. They don't attract another one. But I'm going to expose this pin to a magnet. So now this pin gains a magnetic property, magnetization. Then it will start attracting another pin. And after that, I am going to remove this external magnet. We expected it to release, but it didn't. Because these pins are keeping their magnetic property for some time, because these regularly arranged domains do not turn back to original state as very quickly. It takes time. I think 2020-21 we put it on the board, and then some students said that it stayed like this weeks. Yeah, it's happening. You can state. Okay. So magnetic hysteresis is important. It is a ministry question. The first ministry question. Open ministry exam question by and see the first question. It says that when the applied magnetic field on a ferromagnetic material means like iron, cobalt, nickel, they are called ferromagnetic, and they can be magnetized easily. Ferromagnetic materials such as piece of soft iron is removed. This material retains some of its magnetization, so this phenomenon is called magnetic hysteresis. Okay. Another question, sectional question. When a bar magnet is broken into two pieces, how many poles would each piece have? Again, two. Now this is a magnet with S and M pole. Then I'm going to break this magnet. It is broken already. Still didn't break this. When they're, and then I combine them by using a tip. Okay, now it's broken. Still, it has two poles because poles of the magnet is gained because of the domains. Domains have poles. When you break a magnet into two, still there are domains with M pole and S poles. Still there are domains with M pole and S pole. That's why it will have again two poles. It doesn't matter how many times you break a magnet. Always this magnet will have M pole. But what happens is this: when you break a magnet, you are decreasing the number of domains. Say that in here we have 1,000 domains is a number. 10,000. 10,000 also. When you break them, it becomes 5,000 and 5,000. As number of domains are decreasing, stronger the magnetic field, because this magnet becomes weaker. That's why don't break them, okay? But it's broken. It's not that strong. When we combine them, it becomes stronger. We combine them. Okay. So, and pattern of magnetic field around a magnet. This is a magnet. When I hold this magnet close to a pin, you observe that it reflects. Why? Because it produces a magnetic field around. But do you see the magnetic field with naked eye?
No.
Do you see it? But we can make it visible. We can make this magnetic field visible by using iron filings. Why iron? Because iron is a magnetic material. It can be attracted by a magnet. Okay. So, magnet is composed of domains. Domains have antpole and S-pole. For that, as a magnet has also antpole and S-pole. But if it is not marked with red and blue, generally red is always N, blue is S. Sometimes this is blue, sometimes black, sometimes white, but N is always red. It is certain, I know it, but what if it is not certain? What if it is not polished? What am I going to do? So, to see the magnetic field direction, I have to spread some iron filings around this magnet. So, when some iron filings are spread around the magnet, these iron filings are aligned in the direction of the magnetic field of the magnet and form a pattern. See that this video shows about this. There is a plate. On this plate there are some iron filings, and there is a magnet under the plate. When plate approaches the magnet, yani şunu yapıyorlar. They are doing like this. On this paper they are putting iron filings, putting the magnet below, and then after that you make them closer. When you make them closer, you are going to see that iron filings on the paper will make some shape, some pattern. So this pattern will be representing magnetic field pattern around this magnet. So let's see this movie. Okay, so then it is going to be, this plate will be approaching to the magnet and see what happens.
Sure, there's the dog on the video. That's
Really? What?
It freeze?
No, it must continue. Okay. What? Okay, you see that? This pattern is representing the pattern around this magnet, which we cannot see it by naked eye, but we can make them visible by using iron filings. Okay, but what did you observe in here when you are checking this pattern? These patterns has a regular shape. Yani it seems to be leaving one end, goes to other end of the magnet. One end to other end. And at the ends, these iron filings are accumulating, which means magnetic field lines are, magnetic field is leaving from one end, goes to another end, or vice versa, here to there or here to there. We don't know, but we will learn now how to determine that. Okay, so but I know that pattern is going to look like this. It's going to be looking like this around the magnet, pattern of the magnetic field. Lines looks as if start from one end, goes to ends at another end. However, it's not like this. These loops, they make a loop. They have no start, no end. Because loop has no start, no end. For that reason, we are going to say that magnetic field lines of a magnet continue their path within the magnet, not only outside, they are also inside. So form loops, no end, no beginning, like this. You see the loops? So, loops are outside, a part of the loop is outside, a part of it is inside. A part of the loop is outside, other part is inside. But still no direction. Because the magnetic field is a vector. How can we determine the direction? We should determine the direction. The direction of the magnetic field is determined conventionally. Conventionally means one end of the magnet, scientists, physicists named as N-pole, other end is named as S-pole. And we could give a different name. For example, one end we can say honey, the other hand we can say Lara and honey. we could do like that. It's just the naming. They named N and S. Which side N is going to be set, which one is S? Now we are going to see that. But we saw that magnetic field lines accumulate at two ends, and these two ends are called poles. One end is N pole, other end is S pole. Because magnetic field is a vector quantity, it's given a direction conventionally. It is considered that magnetic fields are living from N pole and enters to S pole. So outside is from N to S, or inside from S to N. N to S outside, S to N inside. So lines of the magnetic field around the magnet is from north to south pole outside and south to north pole inside and forms a loop. But still I am not sure for any magnet which side is N pole, which one is S pole. Yes, I know from N to S, but where is N? Which side? If it is not written, how can I know that? So to know the pole of a magnet, which one is N, which one is S, we need to use a compass. Compass is going to be used to determine the direction of the magnetic field at any place around the magnet if you want to know it. So determine which side is N pole, which one is S pole. We should use a compass, another magnet, but another magnet with known poles. Which one is S, which one is N? We should know. Then we are going to use this known magnet to label unknown one. Okay. So compass. Compass consists of a tiny magnet. Yes, inside this is a compass. If you look carefully, you are going to see that inside a magnet, very thin magnet with red and blue white end. Red one is N pole. Blue, white is S. So it's a natural magnet. And it is inside a fluid. Fluid is just not to decrease the friction. They use this fluid. Then it can easily rotate. Because magnetic field sometimes is not so strong. So it must be very easily rotated. Okay. So compass consists of a tiny natural magnet with N pole and S pole. Red is N. White is S. And this tiny magnet is sometimes called needle. Sometimes called needle. Yeah, this is needle. Needle of a compass. So, but how can we determine the magnetic field direction by using a compass? If you put a compass inside an external magnetic field, I want to know, for example, in this classroom, Earth is a magnetic field? Yes, Earth is a magnetic field. But in my seat, in my position, in which direction is the magnetic field of the Earth? If I want to know, I am going to use a compass. So, if you put a compass inside an external magnetic field, like Earth's magnetic field, the compass will start rotating until needle's magnetic field becomes in the same direction of external magnetic field. Like this. This is needle. Needle is its natural magnet. Its magnetic field from the S to N outside, pardon, N to S outside, S to N inside. Field of magnet, it is S to N. Put this magnet in external magnetic field. This is say that Earth's magnetic field. When you put this compass inside this magnetic field, this compass needle cannot stay like this because no two magnetic fields never cross each other. Now look at now. Blue magnetic field is compass magnetic field. Red magnetic field, external magnetic field. So they are crossing each other, but they don't want to cross. What should happen? One of the magnetic fields should rotate. Which one will rotate? Earth magnetic field rotate or compass magnetic field rotate? Of course compass. It's free to rotate. Compass will start rotating until both magnetic field becomes in the same direction. Now it will stop rotating. No rotation. Then look at the end pole of the compass. Red end. In which direction red end points? To the right. Is it the same as the external magnetic field direction? Yes. When you put a compass at any location, end pole of the compass always shows you in which direction is that magnetic field. Just check end pole. Like this. This is the natural magnet, huh? Now I'm going to know, I will know what is the direction of the magnetic field in here. I will put a compass. You see that? And pole shows down. At this position, magnetic field is down to the ground. Now I'm changing position. Now magnetic field is to the right at this position. Now at this position, up. At this position, left. At this position, down. So as you see, magnetic field around the magnet is continuously changing, just we saw in the drawing also. So by putting the compass at any location, so we can see in which direction is the magnetic field at that location. This is all for today. We'll continue next week.